Welcome. In modern software architecture, performance is not just about raw speed. It's about predictability, startup time, and runtime efficiency. A fundamental yet often overlooked aspect of this is how our applications link to shared libraries. Today, we will conduct a deep dive into the performance trade-offs between lazy and immediate binding in dynamic linking, providing the insights necessary to make informed architectural decisions for large-scale systems. By the end of this session, you will be equipped to, first, differentiate the mechanisms of immediate and lazy binding in the context of dynamic linking. Second, analyze the specific performance implications of each binding strategy, particularly concerning application startup and runtime execution. And finally, you will be able to evaluate the architectural trade-offs and select the appropriate binding strategy based on system requirements such as real-time constraints, security, and user experience. Before we compare binding strategies, let's solidify our foundation. Dynamic linking defers the binding of shared libraries until an application is loaded or even until a function is first called. Unlike static linking, which bundles all library code into the final executable, dynamic linking allows for smaller executables, shared memory usage, and easier updates to libraries without recompiling the main application. The dynamic linker, or ld.so, is the system component responsible for locating these libraries and resolving the symbolic references between them and the application at runtime. This process of resolution is where our choice of binding strategy becomes critical. Immediate binding, often enabled by setting the environment variable ld_bind_now to a non-empty value, forces the dynamic linker to resolve all symbols at application load time. Before the program's main function is ever executed, the linker meticulously scans the executable and its dependencies, finds the address of every required external function and variable, and writes these addresses directly into the global offset table, or GOT. This creates an initial, one-time performance cost during startup. The primary benefit here is predictability. Once the application is running, there are no further delays associated with symbol resolution. The performance profile of immediate binding is characterized by a trade-off. The pro is runtime predictability. Since every symbol is resolved up front, there are no first-call latency spikes. This is critical for real-time systems, high-frequency trading platforms, or any application where consistent low-latency response is paramount. The con, however, is a significantly slower application startup. For large applications with thousands of symbols and numerous dependencies, this initial loading phase can become a noticeable delay for the end user. Furthermore, it might resolve symbols for functions that are never even called during a particular run, performing work that provides no value. Lazy binding is the default behavior on most Unix-like systems for a reason. It prioritizes fast startup. With lazy binding, the dynamic linker doesn't resolve a function's address until the very first time it is called. This is cleverly managed through two structures, the Procedure Linkage Table, or PLT, and the Global Offset Table, or GOT. Initially, a PLT entry for an external function points back to the dynamic linker itself. The first time the function is called, this indirection invokes the linker, which finds the real function address, patches the corresponding GOT entry, and then jumps to the function. All subsequent calls go directly to the function via the now updated GOT, bypassing the linker entirely. The performance profile of lazy binding is essentially the inverse of immediate binding. Its primary advantage is rapid application startup. The initial workload is minimized, allowing the application to become interactive much more quickly. This is highly desirable for desktop applications, command line tools, and services where initial responsiveness is key. The disadvantage is the potential for non-deterministic runtime latency. The first call to any given function will incur a small but measurable delay while the linker performs the resolution. In most applications, this is imperceptible, but in a tight loop or a performance-critical path, this first call penalty could introduce jitter. So, which strategy should you choose? It is a classic architectural trade-off. For systems requiring hard real-time guarantees or absolute performance consistency, Immediate binding is the superior choice. The predictable runtime behavior outweighs the slow startup. Conversely, for user-facing applications where startup perception is critical, lazy binding is almost always correct. There is also a crucial security dimension. Immediate binding is a prerequisite for a security feature called full rel-row, or read-only relocations. By resolving all symbols at load time, the GOT can be made read-only, preventing certain classes of exploits that attempt to overwrite function pointers in the GOT to hijack program execution. Let's take a moment to review. Consider these two questions. First, an application for a medical imaging device requires guaranteed, consistent processing time for each data frame. Which binding strategy is most appropriate? A. Lazy binding, B. Immediate binding, or C. Static linking? The correct answer is B. Immediate binding, for its predictable runtime performance. Second, what is the primary security benefit of using immediate binding? A. It encrypts library calls. B. It enables the global offset table to be made read-only. Or C. It runs the application in a sandbox. The answer is B. It's a prerequisite for full RELRO, which protects the GOT. In summary, the choice between lazy and immediate binding is a nuanced decision that directly impacts system performance and security. Lazy binding offers the significant advantage of rapid startup, making it the default and correct choice for most general-purpose applications. Immediate binding, while penalizing startup, delivers the deterministic runtime performance and security hardening essential for real-time and mission-critical systems. As architects and engineers, understanding this fundamental trade-off allows us to build more robust, efficient, and secure systems tailored precisely to their operational requirements. Thank you.